This is the beginning of Chapter 6, and it introduces intermolecular forces. Intermolecular forces are the attraction between particles. Okay, so what we've talked about prior to this are intramolecular forces, and that are chemical bonds. That's the attractive forces within one single molecule. Okay, so this is the attraction between molecules. Intermolecular forces, and they are abbreviated IMF, again, are the attraction between molecules. That has a huge impact on the state of matter and the properties of a compound. So if you look at these three comparisons of a solid, liquid, and gas, in a solid, and you hopefully remember this maybe from prior science courses, that in a solid, the molecules or particles that make up the solid are packed very close together. The reason that they are close together is that the intermolecular forces are strong. Okay, so just like you get closer to something you're attracted to, molecules do too. And the reason that gases are because the intermolecular forces of gases are weak. Okay, so they don't have any strong attraction to each other, so there's quite a bit of space, and that's why they are a gas. So just to kind of summarize, strong intermolecular forces result in solids, medium, and liquids, and weak intermolecular forces are characteristic of gases. There are three primary types of intermolecular forces. I should say three common types of intermolecular forces that you hear about the most. And the weakest of these are called London dispersion forces. Some will just call them dispersion forces. All atoms and all molecules experience London dispersion forces. And London dispersion force is just an instantaneous weak attraction between molecules. So, for example, if you have a nonpolar molecule, there's no permanent dipole, so you don't have like a partial positive end and a partial negative end that can be attracted to other charges. But you can have, and that licking in the background is my dog, not me, just saying. Okay, so, but you can have temporary disruptions, even in a nonpolar molecule, and I have diagrams of that later. You can have the valence electrons in it, if they're loosely enough held, just kind of shift over to one side for a split second, which gives a temporary dipole to the molecule. So anyway, that's London dispersion forces. Then medium in strength are dipole-dipole attractions. These are present only in polar molecules. So the exercise we went through figuring out shape and then whether the molecule overall is polar, only polar molecules, only molecules with a permanent dipole experience dipole-dipole attraction. Now, the strongest of these is called hydrogen bonding. Hydrogen bonding, I hate that they call it hydrogen bonding. It's not a regular intramolecular bond, okay? It's an intermolecular attraction between molecules. But it is the strongest of the three common types. It is a type of dipole-dipole. Okay, so in order to have hydrogen bonding, you've got to have a polar molecule. So obviously the molecule also has dipole-dipole. But it's an especially strong dipole-dipole attraction that only occurs when a hydrogen atom is attached directly to either a fluorine, an oxygen, or a nitrogen. And that's because nitrogen, oxygen, and fluorine are so electronegative, okay, that they make the hydrogen atom they're attached to quite electropositive. That sets up a pretty strong dipole between hydrogen and one of these three atoms it's attached to, and that makes for extra strong electrostatic attraction. The other half. So I'm going to talk about each of these three common ones one at a time. And as I said before, all molecules and all atoms experience London dispersion forces. Again, those are temporary. So for example, say this is just an atom. Okay, you can't really talk about the polarity of one single atom, right? But it could be if the electrons in this atom, again, are loosely enough held that perhaps they'll shift for just a moment. Let's say we have two valence electrons in this make-believe atom, and that just for a minute they shift kind of close on the same side. And so for a moment, you're going to get this atom with a partial negative side and a partial positive side. We call that an instantaneous or temporary dipole. And because of that, that's going to induce temporary dipoles in other nearby atoms that it encounters. And the strength of the London dispersion force depends on the size of the atoms and molecules. You'll see that the larger atoms and molecules have stronger London dispersion forces, okay? And also the shape, and I'll show you an example of that. And this is probably the most important thing to understand about London dispersion forces, is the more loosely held the valence electrons in the substance is, the stronger the London dispersion force than it is of halogens. All right, so let's talk about some of the variables involved in the strength of the London dispersion force. Compare these halogens. Now, I don't know if you remember or learned this from high school, but halogen, the elements in group 7A, exist as diatomic molecules. Okay, so they always come as twins. Now, I want you to look at the relative boiling points. Why is it getting harder and harder and harder to boil as we go down the period of halogens? What happens when we boil anyway? Okay, we don't break any chemical bonds when we boil or freeze or melt something. All we do, and this is important to understand if you don't already, so let's say that this is one molecule of iodine, here's another molecule of iodine close by. All we do when we boil or melt something is we increase the distance between separate molecules, okay? And remember the first slide I showed you where I said gases, the particles are far apart, solids, they're packed tightly. So all we do when we boil something is we're separating, we're increasing the space between molecules. So how do you get something to boil? Well, to get something to boil, you have to loosen or break the intermolecular attraction. Okay, so what this high boiling point is telling us is that it's harder to break the intermolecular forces of iodine than it is to break the intermolecular forces of any of these other halides. Halogens, bromine, chlorine, and fluorine. Why would that be? Okay, if it's harder to break the intermolecular forces, what does that mean? That means the intermolecular forces are stronger for iodine. Why? Okay, so that's, if you remember in the last slide, I had told you that the larger an atom or molecule is, the stronger the London dispersion forces are. Well, what's the largest molecule in this chart? It happens to be, well, astatine or iodine, the bottom ones, right? And so why does that give for stronger intermolecular forces? That's because in larger atoms, the valence electrons are farther away from the nucleus. Okay, they're more loosely held because they're farther away, right? They feel the attraction of the nucleus less. And because they're more loosely held, they can have these temporary dipole moments. We call that polarizability, okay? The easier it is to shift valence electrons around for a moment, the stronger the London dispersion forces are, and we say the more polarizable they are. And in addition to the size of a substance affecting the strength of the London dispersion force, the shape is also quite important. And that makes sense. So the three compounds that we're comparing here, you can see that the first one, pentane, is just kind of long linear, like a piece of spaghetti or something, right? And then the middle one, methylbutane, has the same exact chemical formula, same number of carbons and hydrogens, but now instead of being a long straight line, it's got a branch. And then the one on the far right is branchy, like just a bunch, right? And so the one with, look at the boiling points. That's how you can always tell strength of intermolecular forces. Okay, so the linear one has a higher boiling point. What does that mean about intermolecular forces? The higher the boiling point, the stronger the intermolecular force, right? Because it's harder to separate the molecules. So why would the one on the left have stronger intermolecular force? Linear shapes do, because there's more contact. So remember, the intermolecular forces are between molecules, right? And so if you imagine lining up a bunch of these molecules, there are several contact points they can have with each other. And so there's a much stronger attraction. You start introducing side groups or branching, two molecules can't get as close to each other. Okay, so the attraction between them is not as strong. All right, so that's it for London dispersion forces. Now we're going to move on to dipole-dipole intermolecular forces. That's the moderate strength, and that only occurs in molecules that have permanent dipoles. Okay, so this is one of the reasons it's important to be able to predict whether a molecule overall is polar or nonpolar, because polar molecules are going to have much stronger intermolecular force because they have permanent developed partial positive and partial negative ends. They have an uneven distribution of electrons, and therefore they build up little charges, and those little charges are attracted to the opposite charge on a different molecule. So that's a stronger electrostatic attraction than the temporary attractions you see with London dispersion forces. So let's look at a couple examples. Formaldehyde, we've talked about that before. That is a polar molecule. The carbon-oxygen bond is polar, and this molecule is not symmetric overall on all planes. So the molecule is polar. All right, so just make note of the boiling point. Then let's compare to that another molecule that has almost equal molecular weight. Okay, so about the same size. But now this is a nonpolar molecule, okay? It is symmetric, but you don't even have to look at symmetry because the carbon-hydrogen bonds are always nonpolar. So any hydrocarbon is a nonpolar molecule. Look at the difference in boiling point. So this is a much lower boiling point for ethane, okay? Much lower boiling. What does that mean? That means weaker intermolecular force. Why? Well, a nonpolar molecule cannot have dipole-dipole, so the only intermolecular force ethane has is London dispersion force. And formaldehyde, since it is a polar molecule, it has London dispersion force like all molecules and atoms do, but more importantly, it also has dipole-dipole attraction because it's polar. And because of that stronger attraction of these molecules to each other, they're held closer together, it takes more force to separate them. And so the melting point and boiling point are both a lot higher than they would be for the nonpolar molecule. All right, so comparing polarity versus boiling point. So hopefully you remember that if something has a dipole moment, it means it's polar, right? And the larger the dipole moment, the more polar it is. Okay, so the most polar of the compounds shown on this table is acetonitrile, the bottom one, because it has the highest dipole. So that means the intermolecular forces between acetonitrile molecules are strongest, right? Which means it takes the most energy to separate those, okay? And that's what you need to do to boil or melt something. So this should have the highest boiling point. Let's see if that happens. Yep, highest boiling point. And here's the only completely non-polar substance, because it's a hydrocarbon, that's close to zero polarity. We'll assume it's close enough, we'll call it zero. And its boiling point is a whole lot lower. Hydrogen bonding is the strongest of the three common intermolecular forces we talk about. And what I've always told my students is hydrogen bonding is fun. Okay, just to kind of remember that it only occurs when there's a hydrogen atom directly bonded to either a fluorine, oxygen, or nitrogen. And so the intermolecular forces of hydrogen bonding are typically shown using a dotted line. I wish they didn't have the black dotted lines. I wish they had those solid here. Okay, I'm going to make all the chemical bonds solid. Okay, so what's left here, that's the intermolecular force hydrogen bond. That one, the red dotted line, okay? So although the hydrogen technically belongs to the NH3, the ammonia on the right, it is very strongly attracted to the lone pair of electrons and the different NH3 molecule. Okay, so let's look at that again. Okay, so the red dotted lines represent hydrogen bonding. This hydrogen actually belongs to the water molecule, right? But it is strongly attracted to the lone pair on another compound in the mixture, okay? And that's always the case for hydrogen bonding. It is between a hydrogen atom that is directly bonded to fluorine, oxygen, or nitrogen, being attracted to a lone pair of electrons on another molecule. So obviously, lone pair of electrons are, we could call them partial negative, right? They're very electron rich. And these hydrogens are very electron poor, partial positive. And so you end up like, look at these, this is just water, okay? So let's just circle the individual water molecules. Okay, these are the individual water molecules, and the rest of it is hydrogen bonding, all the dotted lines. But that explains, hydrogen bonding explains so many unique properties of water, okay? Because of the really strong intermolecular force, water should be a gas. I mean, other molecules that are as small as that are gases, but it's a liquid because of that really strong intermolecular force. It also explains I especially like this comparison for the effect of hydrogen bonding. So let's look at the bottom line, the one right here. So what this does, it shows you the boiling point of a compound, and then we're moving down period 4A. So where we have carbon in the second period, and then below it is silicon, germanium, okay? And the boiling point goes up as they get larger, like you would expect, okay? Silicon's larger than carbon, so you would expect an overall higher boiling point, and you have it. And so that's the general trend, you know, as you go, as your molecule gets larger, you see an increase in boiling point. But now, and sorry about all these scratches here, kind of messed it up, but what's going on here? Look, NH3, hydrogen fluoride, and water, okay, they should be down here with their boiling points if they're going to follow the trend we saw with period 4A. But these three guys have an incredibly high boiling point, much higher than even the larger molecules in their same group, vertical group. So why is that? That's because these three can hydrogen bond, okay? Fluorine, oxygen, and nitrogen, if there's a hydrogen directly attached to them. And so that hydrogen bonding makes that much difference in boiling point. So water, for example, should have a boiling point in the negatives. It should be a gas, okay? But instead, its boiling point is 100, positive 100, okay? And that's just from hydrogen bonding. Hydrogen bonding I mentioned before, but it's also critical in DNA, holds the different strands of DNA together. And again, just to kind of remind you, hydrogen bonding is shown using a dotted line to indicate it's not a real chemical bond, it's an intermolecular attraction. So the hydrogen belongs to the nitrogen, right? But it's strongly attracted to the lone pair of electrons on an adjacent oxygen. And that holds the DNA strands together, which are obviously important. So I'm going to work this example for you, or walk you through it, whatever. So this is just an old multiple choice question from some old test. So it wants you to compare each of two compounds and identify which substance in each pair has the stronger intermolecular force, and then you should be able to explain why too. Okay, so what you're generally going to have to do is to determine what type of intermolecular force they have. So you're going to have to draw a Lewis dot structure. Everything starts with Lewis dot. Okay, so boron has 3 valence, and halogens each have 7 valence. There are 3 of them. So this guy on the left, boron trifluoride, has 24 valence electrons. Okay, and the one on the right, that's 3 for boron, and it's the same, right? It's just comparing bromine versus fluorine. Okay, so they both had 24 valence electrons. So if you draw the Lewis structure of those, regardless of whether you do it with fluorine or bromine, you're going to get the same structure. And we're going to use all 24 valence electrons, just giving the outer atoms an octet. We've used all 24 electrons now. The boron doesn't have an octet, but that's okay. You have to remember boron is a moron, right? Boron is one of the exceptions. It's happy with 6 valence electrons. So that is the structure. And so now what is the shape? And why am I asking you to do shape? Okay, because you can't determine if a molecule is polar until you know if it's symmetric or not, right? And so boron has 3 domains, right? So what shape is associated with 3 domains? Trigonal planar. A trigonal planar is a symmetric shape. So you can either it's symmetric along all axes, or you can do my tug of war thing where you pretend you're the boron in the middle and you have 3 fluorine atoms evenly spaced around you pulling with equal force. They are not going to be able to move the boron, okay? So all of these dipoles, although the boron-fluorine bond is polar, and each bond could be shown with a dipole, all of those dipoles are going to cancel out, and that's going to be the same for both of these molecules. They are both nonpolar because they're symmetric. And so now, what type of intermolecular force do you have if you're nonpolar? Okay, it's just London dispersion forces, both of them. All right, which one is going to have stronger London dispersion? Remember, it was size. Bromine is a lot larger than fluorine, and so it's going to have stronger London dispersion forces because its electrons are farther away from the nucleus and they're more polarizable. All right, so bromine wins that one because it's larger. Now let's compare the second two. Looks like we have a polar bond in each of them. So if you were to draw out the Lewis structure for each of these, so each carbon has 4 bonds, right? The first one happens to be ethanol. That's drinking alcohol. All right, and then the bottom one, instead of the OH on the end, has a chlorine. All right, so that's what the structures look like. Now, let's see. So we have polar bonds, and neither one are symmetric, right? So they're both polar. So what type of intermolecular forces do they each have? Well, hopefully you have noticed that the ethanol one has hydrogen bonding. Okay. The bottom one does not have hydrogen bonding. okay, because there's no hydrogen directly attached to fluorine, oxygen, nitrogen. So the bottom one has dipole-dipole. Now, of course, the top one also has dipole-dipole. Everything that has hydrogen bonding has dipole-dipole also, and they both have London dispersion. But by far the most important attraction is the strongest one, hydrogen bonding for the ethanol and dipole-dipole. So the one that has the higher boiling point or strongest forces would be the ethanol. Okay, so this is just a little bit neater explanation for each of those if you want to read over it. I did mention in the beginning of this PowerPoint that there were 3 common types of intermolecular forces: London dispersion, dipole-dipole, and hydrogen bonding. Now, there are a couple more, but they're not as commonly encountered, but I want to mention this, and that is ion-dipole attraction, which is very, very important in aqueous solutions, which obviously chemists and we all work with quite a bit, right? All right, so that's real important. So we know, hopefully, that ionic compounds are some of the most polar compounds we have, fully developed charges. And polarity, just to kind of remind you, it means charge development in something. So it turns out that each type of ion in an ionic compound, remember we have cations and anions, will be attracted to different parts of a polar molecule. So, and most of what we're going to talk about are solutions in water. And as it turns out, most ionic compounds are actually soluble in water because water's polar and ionic compounds are polar. So there's a little saying that says like dissolves like, polar things dissolve in other polar things. But what I want you to get out of this slide is that the reason ionic compounds dissolve in water is because when they do, the cation and anion separate from each other and become stabilized or solvated by water molecules. So I want you to look carefully at these 2 diagrams. What looks different? Now I see both the sodium cation and the chloride anion in the middle and surrounded by water molecules, but there's a key difference in both of those pictures. Can you identify that? The difference is the anions, having the negative charge, are more strongly attracted to the electropositive or partial positive hydrogen atoms in water molecules. So if you see all the water molecules, the hydrogen atoms are facing the anion. Now, on the other hand, the cation, positively charged, is going to be attracted to the opposite charge in water. And so the partial negative end of water would be the electronegative oxygens. So cations are solvated. All of the oxygen atoms of the water molecules will be facing the cation. And ion-dipole attraction is actually stronger even than hydrogen bonding because you have some full development of charge. The ionic compounds are fully charged, so that makes it stronger. All right, just kind of see a summary of everything we've talked about. London dispersion, those temporary dipoles, dipole-dipole attraction for only polar molecules, hydrogen bonding, okay, fluorine, oxygen, nitrogen, and what we just talked about, ion-dipole, and that's for aqueous solutions. This is just a summary slide. I kind of like to summarize things, make sure you know what all the key points are. So I won't read them to you, but they're there. I think I mentioned early in the PowerPoint that intermolecular forces determine a lot of properties about a compound. So we've talked about boiling point and melting point, the state of matter, whether it's a gas, liquid, or solid, but there are several other properties that are affected also by the intermolecular forces. And that is surface tension. Whoops, how I did that there. Let's see. Surface tension is one of them. Something called viscosity. I'm not sure if you're familiar with that, but that is the book definition. It's the measure of a substance's ability to flow freely. So I want you to think of honey, pouring a cup of honey versus pouring a cup of water. Honey has much higher viscosity than water. That's because honey has extremely strong intermolecular attractions, okay? Has lots and lots of OH groups in it. And because of the strong intermolecular forces, honey is very viscous. So the stronger the intermolecular force, the more viscous, if it's a liquid, okay? And then solubility, which we've kind of already talked about, okay? Depending on the strength of intermolecular forces and how polar the molecule is, helps determine its solubility in different solvents. A quick new vocabulary word. So we talk about things being soluble in other things. There's a special word that describes two liquids that are completely soluble in one another, and that is miscible. Looks like it should be pronounced miscible, but it's miscible with an S, okay? And I told you before there's a little saying that chemists use. It's like dissolves like, which simply means polar solutes will dissolve better in polar solvents. And similarly, nonpolar solutes will dissolve better in nonpolar solvents, okay? So an example of two miscible liquids would be water. Remember, the dotted lines just show the intermolecular attraction. Okay, so all of these red and white things are water. And then this is ethanol. Okay, so these on the outside are all water molecules. And ethanol, black always represents carbon atoms. So that's carbon atoms, each with 2 hydrogens. And then, oh, that's ethylene glycol, that's antifreeze. Okay, then OH on both ends of that middle larger compound. All right, so you can see that hydrogen bonding has gone wild here. So the ethylene glycol, antifreeze, I'm sorry, is very soluble in water because it is very polar and capable of hydrogen bonding, and water is very polar and capable of hydrogen bonding, so match made in heaven. That also explains light doesn't dissolve, unlike. So oil, we know doesn't mix with water. Oil is a hydrocarbon, okay? Remember, carbon-hydrogen bonds are nonpolar? And so water is very polar, and so the two don't want anything to do with each other, okay? They won't mix. Almost done here. It's just kind of an interesting comparison for viscosity. So look at all these substances. They're all hydrocarbons. And look at the difference in viscosity. I'll pull that up there. There we go. So obviously, the longer the chain of the hydrocarbon, the more viscous it becomes. So, and the more viscous, just like boiling point, the more viscous means stronger intermolecular forces. So then why would this hydrocarbon on the bottom have stronger intermolecular forces than the one on top? Would you be able to explain that? So I'm going to tell you very, very strongly now. You probably need to jot this down. You need to be able to explain, just like I'm explaining now, why there are differences in viscosity, boiling point, melting point. So how I would explain this, I would say, okay, although all of these molecules are nonpolar, because carbon-hydrogen bonds are nonpolar, so the only intermolecular force they all have, right, is London dispersion forces. And when you're comparing only London dispersion forces, the size of the substance becomes very important. The larger the size, the stronger the London dispersion force. Therefore, the higher the boiling point, the higher the viscosity. All right? So that is it for this lecture. So just to summarize what you need to know, there are 4 intermolecular forces that you need to know what they are, be able to define them. You also need to be able to look at a compound and identify what type of intermolecular forces it has. Sometimes that's going to require making a Lewis dot structure and determining shape and symmetry and polarity. And finally, you need to be able to compare different compounds and explain why one has a different boiling point or viscosity from another in terms of intermolecular forces. That's it.